Alright, so welcome back. So today we want to prove that 30 divides 6n to the 5th plus 15n to the 4th plus 10n cubed minus n for every natural number n. So since this is a sequence of statements involving natural numbers, we want to prove this by mathematical induction. Alright, so we're going to start off in the following way. We're going to say let p of n be the statement "30 divides 6n to the 5th plus 15n to the 4th plus 10n cubed minus n." Alright, so it looks like the first thing I want to do is establish a base case. So that means I want to establish that the statement p of 1 is a true statement. So let's do a calculation. So we've got 30 divides 6 times 1 to the 5th plus 15 times 1 to the 4th plus 10 times 1 cubed minus 1. So when we calculate this, that's going to give us, it looks like 30. So 30 divides 30, that is a true statement. So the statement p of 1 is a true statement. So now for the inductive step. Okay, so we're going to let n equal some fixed k. And we want to assume that the statement p of k is a true statement. So we're going to say assume p of k is true. So what do I mean by that? Well, I'll say, well, that is assume that 30 divides 6k to the 5th plus 15k to the 4th plus 10k cubed minus k. Okay, so we're assuming this for some fixed k, and we want to show that p of k plus 1 is true. And again, just for clarity, I'll say that is. So that is, we want to show that 30 divides this quantity. So we have a conditional here, right, of the form p of k implies p of k plus 1. Okay, so we're assuming this is true for some fixed k, and it's our job to show that this is true. So let's work with this portion right here, and through some algebra and our inductive hypothesis, we're going to show that 30 divides this, that 30 is a factor of this. All right, so let's see what we have here. So we have 6 times k plus 1 to the 5th plus 15 times k plus 1 to the 4th plus 10 times k plus 1 cubed minus k plus 1. So we're going to go ahead and expand this. If you need to, on the side, it might be helpful to write out Pascal's triangle, at least to the fifth power coefficients. Okay, and that's all we need for the coefficients. So yeah, let's go ahead and expand this out. See how we do for space here. This will be interesting. So I'm going to have, so I'm looking specifically at this row for my coefficients, right? So I'm going to have k to the fifth plus 5k to the fourth plus 10k cubed plus 10k squared plus 5k plus 1. Okay. Okay, so we expand this out with the binomial expansion, our coefficients from Pascal, and then right here. So here I want to look at this row. So I'm going to have k to the fourth plus 4k cubed plus 6k squared plus 4k plus 1. Okay, so now we want to look at this row for this expansion. So we're going to have 10 times k cubed plus 3k squared plus 3k plus 1 minus k plus 1. So a bit scrunched, but hopefully you were able to follow that along. Okay, so that seems pretty good. And let's see if we can start to combine. So let's see here. So I'm looking at combining, let's see here, there's only one k to the fifth. So that's going to be 6k to the fifth. Okay, so let's look at all of my k to the fourths. So that's going to be 30 plus 15. So that's going to be a total of 45k to the fourths. So I think there's only a k to the fourth here and a k to the fourth there. Okay, so I've got so let's look at k to the third. So we've got 60 plus 60 plus 10. So that's going to be 130k cubed. So I'm just going to double check here, right? So 60, 60, 10. Okay, so I think we're fine there. Let's look at our k squares now. So we've got 60. We've got, I believe that's 90. Let's double check that. Don't trust me. You shouldn't either. So 15 times 6 is 30. And so that's 90. Okay. So we've got, so just to double check, we've got 60, we've got 90 and 30. So I think that's 180 in total k squared. All right, so let's see here. Next for our k's, we've got 30, we've got 60, we've got 30, and then minus 1. So that's 119k. And then what about our constant terms? So we've got 6, we've got 15, we've got 10, minus 1. So that will be 30. Okay, so now we want to break this up in sort of a smart way where the inductive hypothesis pops out. And so let's do that. So we're going to split this up. I could really think about this as 6k to the fifth plus 15k to the fourth plus 10k cubed minus k plus, and just think about what's left over so I get this. Looks like 30k to the fourth plus 120k cubed plus 180k squared plus 120k plus 30. So this is nice, right? So by our inductive hypothesis, we know that this is divisible by 30. So I'm going to say that this is equal to, how about 30 times j for some j? And here I'm just going to show the factorization. So how do I know it's equal to 30j for some j? Because our inductive hypothesis says that 30 divides this quantity, right? And that's the definition of divisibility right here. All right, so right here I'm factoring out a 30. That's going to leave me with a k to the fourth plus 4k cubed plus 6k squared plus 4k plus 1. So I'm going to say the move from here to here, so these are the same, but this was by our inductive hypothesis, the fact that we're able to rewrite this. And I really should say that this is true for some integer j. I know it's not ideal to write these little footnotes. So let's say that this wouldn't be my formal proof that I would hand in. I wouldn't have this or this here, but this certainly gives a good sketch of the proof. And so by the definition of divisibility, this is equal to, how about 30m for some integer m? That's, again, by the definition of divisibility. And so this is equal to 30 times j plus m, which is equal to, let's say, 30p, where p equals j plus m, an integer. Well, this was nice because now we have the definition of divisibility. This is equal to this. Well, by definition of divisibility, 30 divides this. So thus, 30 divides this quantity, 6 times k plus 1 to the 5th, plus 15 times k plus 1 to the 4th, plus 10 times k plus 1 cubed, minus k plus 1. Well, there was really nothing super special about my choice of k. K was arbitrarily chosen. So I need to say that. So I'm going to say, since k was arbitrarily chosen, we have, by mathematical induction, that 30 divides 6n to the 5th plus 15n to the 4th plus 10n cubed minus n for all natural numbers n.